Chapter 7, Number 1. A pendulum bob swings from point 1 to point 2 along the circular arc indicated in figure below. So a pendulum is an object that's free to swing around a so-called pivot. So the pivot point here is this. A physical pendulum is a real object. This is an ideal pendulum where we have an ideal string, which is massless and has some length but no mass, no inertia to it, and then something called the bob, which is this thing, which is assumed to also be basically a point-like mass. So even though they draw it as a big circle, they really mean all the mass concentrated at the end of the string, and that's what gives the pendulum inertia. So we'll talk a lot about oscillatory systems later in the class, and the pendulum is sort of the prototypical one. So that's what we have here. In this particular pendulum, they say that it's moving from point 1 through to point 2 along that arc. And they want to know about gravity and the string. So if we pick anywhere along that motion and we draw our pendulum bob, and we say what are the forces that act along that motion, well, there's certainly the weight, which always points straight down, and then there's a tension in the string, and the tension always points radially towards the pivot, inward towards the pivot. The tension is what moves in a circle, and gravity is what accelerates it along that circle, in essence. And we can see immediately that if we remember that our path essentially looks like this, that at this moment the path is, the path is always tangent to the circle. So at this moment, it's perpendicular to the string. In fact, it's always perpendicular to the string, but it's not necessarily perpendicular to gravity. So it actually makes part B really easy. The work done by the tension in the string is 0 because Ft is perpendicular to the displacement at any given moment. Part A is then not hard, but a little bit more involved. We see that gravity has a component that is along the way it's moving, and has a component that's perpendicular. And the part that's along does work because it moves along this. So the work done by gravity there is positive because gravity is partially along. So from the basic definition of work, we know that it will do positive work. We could look at this, when Walker assigns the problem, he hasn't talked about anything but the definition of work. But we can come back and say there's a different way to sort of think about this, which is that the total work done on the system is positive because we know that the bob is going to speed up. We know that whatever the velocity is at the start, it has a much greater velocity over here, which means that delta K is greater than 0. So the total work is greater than 0, but the total work is the work done by gravity because the tension can't do any work. So there's two different ways of looking at it. There's actually a third. You could do it from an energy conservation viewpoint and say that the potential energy decreases. So yet another way to think about this is that delta U is negative because it ends up going down. Right? It has some height that it falls through, and that's minus the work done by conservative forces, so minus the work done by gravity. So if minus the work done by gravity is negative, then the work done by gravity is positive. So not surprisingly, all of these different things end up saying the same thing. They are mutually consistent.